Good morning, everyone. Good afternoon, good evening, depending on where you are connecting to this conference. My name is Stéphane Rainsard. I'm working in China. I'm looking at STM32 ecosystem, security and safety, among other things. As you can see from the background, this video is being pre-recorded, and I'm in fact borrowing my son's desk in order to record that video. I'm trying to make that video as interactive, as entertaining as possible, waiting for the next time when we will be able to do it live. Okay, so let's start. I'm gonna introduce first the STM32. Then I'm going to talk about the STM32 MP1 from a product and an ecosystem perspective, as well as looking into STM32Cube.AI. And for these two elements, I'm going to have some use cases where the STM32 ecosystem is working together with the thread in some interesting ways. So let's get started. In terms of introduction, I'm going to start by the portfolio. In 2007, we introduced the first STM32 Cortex-A MCU, STM32F1, and since then we have been introducing new series. Last year, we introduced the STM32U5, which is our flagship of ultra low power, and also security. I'm going to talk a little bit on the STM32 MP1 on this presentation. That's a very interesting product. But let me first introduce what is a generic ecosystem. A generic ecosystem is everything you need in order to work with an STM32. It is made of hardware development tools, software development tools, embedded software, and services. Hardware development tools, you have our evaluation boards or debugging tools. Software development tools, these are the STM32CubeMX, Cube Programmer, all the tools you install on your computer. The embedded software are the drivers, the OS, as well as the stacks. And in terms of services, you have all the documentations, all the communities, but also all the support and other field services. Now, this ecosystem is built with elements coming from three different sources. You have open source material, you have ST-owned design elements, as well as partners elements. This is what makes the STM32 ecosystem. If we look at the PC software tools and the embedded software, this is part of STM32Cube Software Suite. You have CubeMX, Cube IDE, Cube Programmer, Cube Monitors on the PC software side, and you have the MCU packages on the embedded software side, as well as some Cube expansion. In the context of this presentation, I'm going to talk a little bit about the CubeMX with the MP1, but I'm going to also talk about the expansions with Cube.AI. Okay, so let's start with the STM32 MP1, looking at the product, the ecosystem. So the STM32 MP1 is part of the high performance product series. We also have wireless MCUs, ultra low power MCUs, as well as mainstream MCUs. But the one we are talking here is the STM32 MP1. So just wanted to put that one in context. Now, it's an STM32, which means that it has the same longevity commitment. It also means that it shares a lot in common in terms of ecosystem elements. You can leverage CubeMX, you have Cube Programmer, boards, as well as partners, support, and communities. Now, this is a general purpose MPU for all developers. It does not matter if you are new to MPU, if you are already an experienced MCU and MPU developers, or if you are pure MPU developers. So this is the value proposition. We mentioned about the STM32 legacy values just now, and here are a couple of other elements. The industrial grade qualification on all part numbers, the broad ecosystems with OpenSTLinux distributions, Cube softwares and development tools, as well as partners. There are also elements that makes the product easy to use. Things like the STPMIC1, which is the sister chip power supply chip from ST. We have, as we just mentioned, CubeMX, as well as some options for SOM and system SIP options from our partners. This product has a flexible architecture. So let's get into that part. So you are basically having a Cortex-A and a Cortex-M. On the Cortex-A side, you can run OpenSTLinux distribution, and on the Cortex-M side, you have the STM32Cube ecosystem available for you to use. This is the same, let's say, flexible architecture, but with a little bit more of details. So I have the Cortex-A that I can use for doing high performance graphics and communications with advanced GUI, with all the connectivities that I can use. But I also have the Cortex-M4 that I can use for real time. If I use one of the peripherals, assign it to the Cortex-M4 and connect it to sensors, I can do real-time application. I can do the real-time part of my application on the Cortex-M4. That flexible mapping of resources is what makes the STM32 MP15X an interesting product. Okay, so I talked a little bit about OpenSTLinux, so let's dig into it. ST has a continuous investment in Linux. So ST is a silver member of the Linux Foundation, also part of the Yocto project. One of the inventors of the OpT from ST Ericsson, an active member of OpenAMP, and a club member of Linero. This slide is interesting because it shows the structure of the OpenSTLinux releases and the support scheme. So we have at a given time, we have two kernels. So for example, in 2021, we had the OpenSTLinux based on the kernel 5.4 and OpenSTLinux based on the kernel 5.10. Each of those is getting a 2-year support. And then it's gonna, the support is done through partners. And we are now in 2022, so we have the OpenSTLinux based on the 5.10 kernel, as well as the OpenSTLinux based on the 5.15 long-term support version of the kernel. So this is the way OpenSTLinux is released and supported. Again, after the support is still available from partners. Now, the software tools offer. It's an STM32, so no surprise, we find STM32CubeMX, we find STM32Cube.ID, and STM32Cube Programmer there. The STM32CubeMX is used for the device tree configuration and generation, so it's a configuration tool. You can use Cube.ID for the development of your application, and you can also use the programmer. Please note that you have some of the security elements of the STM32 ecosystem that is using STM32Cube Programmer. So basically, the STM32 MP1 is an STM32. Now, let's talk a little bit about the OpenSTLinux from a distribution and package point of view. You have one distribution and 3 packages. We have a starter packages. The starter packages is to quickly and easily start. Basically, you are getting a package for a given board with a given microcontroller. You take that, you take the STM32 tools, you program this is in one of the STM32 boards. I'm going to talk about the boards just after, but you take one board, you take the starter package, the tools, you program the starter package in your board, and you have a Linux environment running on an STM32 MP1 to get started. Now, if now you need to develop some of your application, keeping most of the starter package elements, I mean a given kernel, etc., then you can start from the developers package. This will give you the flexibility and the SDK to do your own development. Now, if you want to have full control, everything available for you, then you can use the distribution package, and that distribution package is leveraging Yocto, and basically we gave you everything, all the source code you need and the scripts you need to create your own Linux distributions. You can even generate your own starter package and your own developers package from that. So one distribution, 3 different packages depending of what you are looking forward to do. The evaluation platforms, again, it's an STM32, so you have the eval boards and the discovery kits. The discovery kits come in 2 flavors. You have one flavor without a display, and you have one flavor with a display and a Wi-Fi module. And then you have all the hardware available from the partners. So I told you at the very beginning that I'm gonna go through an interesting use case of how you can leverage both OpenSTLinux as well as some of the Artist-Thread ecosystem. We have a flexible platform here with a Cortex-A and a Cortex-M. So OpenSTLinux is gonna run on the Cortex-A, and I'm gonna have Artist-Thread running on the Cortex-M. So if we look at the block diagram, so this is the first slide of that presentation with the block diagram. So you have the dual Cortex-A core here. We have the Cortex-M4 cores, and then we have all the peripherals about connectivity, analog, control with the timers, security, and all the systems. Not to forget the GPU. So in that use cases, I'm gonna have an OpenSTLinux distribution running on the Cortex-A, and I'm gonna have Artist-Thread running on the Cortex-M. Now, what is it that the Artist-Thread can access? What is it that is more on the OpenSTLinux side? So if you look at here, you see the list of the IPs that are supported by Artist-Thread. So all the IPs you see with the red outline are the IPs that have been ported on Artist-Thread. So you can have connectivities. Let's say I have some sensors. I want to use the I2C or the SPIs. They are available. I want to do motor control. It's available. I want to do a little bit of AES on the other thing. That is available. Analog available as well. So basically everything that you would need to make real-time thing is going to be available on the Cortex-M4 with the porting that was done by Thread. The graphics, as well as some of the configuration, is still gonna be under the dual Cortex-A7 control. But basically, this is an overview of the hardware. Now, I have two systems. I have OpenSTLinux and I have Thread. How does this system start? Let's have a look at the boot sequence. Basically, what you see here is that you start on the Cortex-A7. So you have the boot chain here with the secure boot here, as well as TFA, and then you have your U-boot stage. Then your application is you have the runtime services with the trust zone architecture with some secure and non-secure domain on the Cortex-A7. And then you have the Cortex-M4 side. And that Cortex-M4 side is what is running Thread, and you can start it from U-boot, but you can also have Linux starting it. Either at the second job or at the second stage, or you use remote proc in order to load from the Linux kernel. Another element that is interesting and that is showing the actual flexibility of the platform is the communication between OpenSTLinux and Thread. So you have the Cortex-A7 that is going to load the Thread, and then through some shared memory and a dedicated IP, you're going to have some communication between the two. Little more on that after. You can also assign you have a static allocation of the peripherals. So if you, let's say, want to have some sensors on the Cortex-M4 side, then you can assign an I2C or an SPI there. You may want to keep the CAN on the Cortex-A7 side if you want to do communication. Let's have a look now a little bit at how the software is working, both on the Cortex-A7 side and the Cortex-M side. So on the Cortex-A7, we are using well-known software packages to do that. We are using remote proc to control the loading of the Thread package, and then we are using RP message and virt.io for the communication. This is what you see here as well as here. Loading and control being by the remote proc. If I look at the Cortex-M4 side, we are using OpenAMP. In fact, Thread did the porting of OpenAMP on the Cortex-M4 side in order to be able to use it when communicating with the Cortex-A7. I will not go into the details of everything about OpenAMP project, but you have some links here that you can refer to if you want more details. So basically here you have a couple of information regarding the communication between the two. One more important point is about the debug. The debug side, you have the Cortex-A debug. That's where you're gonna find STM32Cube.IDE For example, you will manage your Linux project and you can use STLinux to debug the Cortex-A. The development on the Cortex-M side of Artisthread is gonna be through some third-party IDs. So ST has validated the implementation using IR. Artisthread also has an implementation using Kill. And the debugging is gonna be done through the UART. So I just wanted to give a little bit of information regarding how the debug is working in that multi-project architecture. And what you have here is a simple introduction about how to load Artisthread thanks to remote proc. So you can see here Artisthread is running on the platform. You start it and stop it. So this is actually working. I just gave a quick overview of that. If you are interested in that solution, here are some references. I put some references on the coprocessor management. In fact, this is available on the STM32 wiki. And you have a lot of other information on the STM32 MP1 wiki as well. And also, I put some resources on Artisthread. So one point I want to highlight here is that Artisthread is not part of the default open STLinux distributions, but you can get the source code through GitHub and then get the open STLinux distribution from st.com. You build them, you integrate them together, and you are good to go. ST did the validation of that, so that's actually an interesting use case if you are looking for both high performance on the S7 and as well real time on a Cortex-M. Okay, so in this part I'm gonna talk about STM32Cube.AI. This is an optimized ecosystem, an optimized AI ecosystem for the STM32 microcontroller, for the STM32 MCUs. But before going into the details of what STM32Cube.AI is, I want to go through the key steps behind the neural networks. So first, you need to capture some data. That is the step one. Once you have those data, you clean them, you choose a neural network topology. That is your step two. Then you train your model with those labeled data. That is the step three. This is the model creation. Now, starting from step four, that's where you can use STM32Cube.AI. The step four is to convert this neural network into something that is optimized for a microcontroller. Then you process those data. Basically, you load everything inside your microcontroller in the step 5, and you run your algorithm on the target. So Cube.AI is the step 4 plus 5. Cube.AI is a tool for teams with some AI expertise. Why I'm saying that? Because you developed and you train your model with one of those major frameworks. So I mentioned Tensor, LiteFlow, you have scikit-learn, PyTorch, etc. So you need to know how to use those tools. And then that's where Cube.AI for the step 4 and the step 5 get into the picture. That's where you will get the best performances. That's where you will be able to validate the performances and do this on most of our portfolio. Cortex M0, M0 Plus, M4, M33, and M7. If we look at the same thing a little bit from a different perspective. So this on the left, these are the step 1 to 3. These on the right are the step 4 and the step 5. So you use your major AI framework, or you can use scikit-learn, you export to ONNX format, and then you put this into Cube.AI. Cube.AI will let you select the most appropriate MCU. And you will be able to review as well a lot of the memory consumption layer by layer. That is, I have a slide on that is very interesting. And then you put this into the STM32. You can validate and you can fine-tune it. This is the workflow to implement neural network and machine learning on STM32. Now, let's pause for a moment and look at the STM32 portfolio and our AI solutions. So STM32Cube.AI is available with the latest version, the version 7.1 is available on Cortex-M0, M0 Plus, M4, M33, and M7. So basically, it makes it available for most of our portfolio, including the latest U5, but as well as our high-performance MCU. We also have another tool that is NanoEdge AI Studio. That one is able to work on our complete portfolio. So it's a different offer. I will not go into the details, but definitely check it out if you are interested in AI. We also have some Linux package for the STM32 MP1. So let's go back to STM32Cube.AI. Couple of main features. I want to dimension my system so I can select quickly and configure a microcontroller within Cube.AI. I can review some of the model layers. Then I optimize it. We are optimizing all the elements that can be optimized on the system. The memory, the code execution. We support quantized models. We optimize for performance. We optimize for RAM usage. We use Lite runtime libraries. And then you fine-tune it. You can split, for example, between internal and external memory, depending on how your architecture is done, or if you want to compare internal versus external memory. This is all the features of STM32Cube.AI. And it is available both as a graphical and a command line interface tool. Another interesting about STM32Cube.AI, or more about AI on the STM32, is that you can have a flexible implementation when you run TensorFlow directly on the STM32, or you can go for the more optimized approach where you use Cube.AI, and what you run on the STM32 is actually the output library that run only on STM32, by the way, because we optimize it for our product. And this is where you're gonna have a really optimized model running on your target. I will come back a little bit of the performance and the difference of the performance between these two in the next part of my presentation. Fine-tuning. So STM32Cube.AI, as I said, you can see the memory, the RAM consumption for each and every layers. That's what you have here on the left. You can also have advanced settings, enabling the use of external memory, enabling the use of non-contiguous external memory. You can even optimize input buffer to reuse them as activation buffer at runtime. All those types of configuration is available for you to fine-tune your implementation on the STM32. Very powerful tools here. But this is just an introduction. This is just an overview. If you want, you can get more tools and documentation from st.com website. I just mentioned, I'm talking for 5-10 minutes now about performance optimization. Let's have a look. So I just presented that slide already when you have TensorFlow Lite running on the STM32 on the left and the library being optimized by Cube.AI on the right. So I can take one model, run it on both strategy, and then see what the outcome is. And that is exactly what we did. So what you have here are two models, one of image classification, one of visual wake word, running on two different platforms, a U5 microcontroller for the first model and an H7 microcontroller for the second model. The first row is the Cube.AI optimized library running on the target. The second line is TensorFlow Lite interpreter running on the target. And what you can see is that in both examples, we get faster inference time, smaller flash, smaller RAM. So I just wanted to have a little bit of data just to show you the type of performance gain you can get on when using STM32Cube.AI. And in fact, this is also one of the reasons why Artistthread is using STM32Cube.AI. So that's what I want to talk a little bit now, is that how is Artistthread in their AI kit using STM32Cube.AI. So if you remember my first slide about the steps, so you have the step 1 to 3 that are at the bottom part of your flow. So you start to look at this slide from the bottom left. You use PyTorch TensorFlow, you build your model, you train your model. Step 1 to 3. Then step 4 is you are using an AI kit tool to optimize your model for the target. And what Artistthread AI Toolkit is doing is they are using STM32Cube.AI. They are using the command line version in order to leverage the optimized performances. And what you get is the Artistthread environment with both an optimized AI as well as all the other elements, operating system, etc. So this is the toolset part. Now, if we look at the embedded software part, that's where we get an STM32 target device here, running the optimized Cube.AI library. We have the Artistthread APIs, and you have your model running on top. This is another example, this is another very interesting example on how the STM32Cube.AI is being leveraged by an external tool like RTAK, for example. Okay, so let's have a look at a couple of references for what we saw about this RT-AI kit and STM32Cube.AI. So here I listed 3 GitHub repositories where you can find some of those examples. Most of them are using the ArtPy, which is the board you can see on the right. Short takeaway, we talk about STM32 MP1, its flexible architecture. We talk about its ecosystem being an STM32. We talk about Artistthread and OpenSTLinux running on an STM32 MP1.5 with OpenSTLinux running on the Cortex-A7 and Artistthread running on the Cortex-M4. And I touch a little bit on the STM32AI. We are making AI on all our portfolio. NanoEdge AI Studio is being one tool. I didn't talk too much about that one, but I recommend you to check it out. And I show a little bit more about STM32Cube.AI and the optimization it brings to the table. And the last diagram shows how another use case of Artistthread and STM32 being used together on an STM32 to bring the best to our customers. And for sure, if you want more inputs on the MPU or the AI solution from ST, you can always get to st.com. So, thanks a lot for your time. I hope you enjoy the rest of the Developers Conference. Thanks again. Have a nice day and take care.